Hello viewers, welcome to Career Guidance DSP playlist. So in this video, we are going to see about effect of code word length due to quantization of filter coefficient. So due to this quantization of filter coefficient, what are the effects we have? We are going to discuss this. Here the question is the system function is given as an h of z is equal to 1 divided by 1 minus 0.5 z inverse into 1 minus 0.45 into z inverse. That is, study the effect of shift in pole location with a 3-bit coefficient representation in direct on the cascade form. So, the system has been realized in direct form, either in direct form 1 or in cascade form. If you realize the system in direct form 1, what be the shift in the pole and what be the poles in the cascade after the quantization. We are going to analyze the same. Here for quantization, there is a 3-bit truncation is used. Okay. First, the first step is that is for direct form. That is a direct form. So before direct form, so you must find the what is the poles. What is the actual poles? That is 1 divided by 1 minus 0.5 into z inverse into 1 minus 0.5 into z inverse. I am taking z inverse common outside, so that it is 1 by z inverse z minus 0.5, again z inverse z minus 0.45. So z power minus 1 into z power minus 1 is z power minus 2. So when it goes to numerator is z square divided by z minus 0.5 into z minus 0.45. So initially my poles are, so before quantization process, initially my poles are P1 is equal to 0.5 and P2 is equal to 0.45. Okay. So before quantization process, my poles are P1 is equal to 0.5 and P2 is equal to 0.5. So when we realize the filter using direct form 1, what be the change in the filter coefficient? That is by direct form 1. So h of z is equal to 1 minus 0.5 into z power minus 1, 1 minus 0.45 into z power minus 1. You just multiply it. So 1 minus 0.45 into z power minus 1 minus 0.5 into z power minus 1 minus into minus plus 0.5 into 0.45, it is 0.225 into z power minus 2. It is equal to, so after simplification, 1 minus 0.95 into z power minus 1 plus 0.225 into z power minus 2. Here, so for this, the transfer function h of z is equal to 1 minus 0.95 into z power minus 1 plus 0.225 into z power minus 2. Here, we are going to apply the quantization for this filter coefficient. So after applying the quantization for this filter coefficient, what be the change in the transformation? Let me see. That is, I am applying this. This is equal to, I am applying the quantization process 1 minus quantization of 0.95 z power minus 1 plus quantization of 0.225 into z power minus 2. Okay. The quantization process, that is the quantization process, in quantization process, that is a 3-bit truncation. First convert the decimal into binary and then apply the 3-bit truncation. After apply the 3-bit truncation, again convert into decimal. So this is the process of conversion process in the quantization. That is first for 0.95. So it is in decimal, you have to convert into binary. So how to convert into binary? We just multiply the value by 2. That is 0.95 into 2, which is equal to 1.9. Again you have to take 9, that is 9, you have to take 9 again by 2, 1.8, again 0.8 into 2, 1.6, again 0.6 into 2, 1.2. Here 3-bit truncation, so you just go up to 4 values. So you have to choose you have to choose this. So the binary conversion is 0.111. So apply the truncation process, that is 3-bit truncation. So after 3-bit truncation, that is 0.111. Okay, again convert this into decimal. So how to convert this into decimal? Very simple, that is 0.111, 1 into 2 power minus 1, 2 power 1 into 2 power minus 2, and then 2 power minus 3. Add all these things, 1 by 2 plus 1 by 4 plus 1 by 8. When you add all these things is equal to 0.875. So decimal value. Similarly, do it for 0.225. Similarly, do it for 0.225. Again, for 0.225, multiply by 2 is equal to 0.45. 45 into 2 is equal to 0.9. 0.9 into 2 is equal to 1.8. And then 0.8 into 2 is 1.6. So you have to choose the point as 0, 0, 1 and 1. That is the conversion 0.0011. You have to convert this that is after 3-bit truncation, the equivalent value is 0.001. Then you have to convert into decimal. For 0.001, that is 0.001, 2 power minus 1, 2 power minus 2, 2 power minus 3. Add all these things, 0 into 2 power minus 1, 0, 0 into 2 power minus 2, 0, 1 into 2 power minus 3, that is 1 by 8. That value is equal to 0.125 base 10. Okay, so from this my new filter coefficient after quantization process is, that is, so my new transfer function after quantization process is h of z is equal to 1 divided by 1 minus, what is this, after quantization of 0.9, after quantization of 0.95, it is for 0.95 it is 0.875, 1 minus 0.875 z power minus 1. And similarly for 0.225 after quantization process, it is 0.125. So h of, that is the new transfer function after quantization process, is h of z bar is equal to 1 minus 0.875 z power minus 1 plus 0.125 into z power minus 2. Okay, so you have to find the new poles after the quantization. So for this I am just taking z square, that is I am just taking z power minus 2 common outside, that is 1 by z power minus 2 is z square plus 0.875 into z, sorry, minus 0.875 into z plus 0.125. So z power minus 2 is equal to z square divided by z square minus 0.875 z plus 0.125. So for this, the new poles are, that is z minus 0.695 and z minus 0.179. So these are all the new poles. You just apply the formula minus b plus or minus root of b square minus 4ac divided by 2a, or you can find the roots of the equation by using the calculator. Okay, so in that calculator, press equation mode and then again press degree 2. So in that, for a value put 1, b value as minus 0.875 and c value is 0.125. When you press next equal to, it gives the first root value and the second root value. So from that, my new pole locations are 0.695 and 0.179. While I am comparing with the actual poles, the actual pole is P1 is equal to 0.5 and P2 is equal to 0.45, where after quantization process it is 0.0695 and the 0.179. So from this, by comparing with the actual pole, that is after quantization, the poles are far away. The poles are far away from the actual value, or deviation is more. So this is about the analysis of a filter, that is a pole location, if the IR filter is realized in direct form. Suppose if the poles are realized in cascade form realization. So in cascade form realization, that is h of z, the given transfer function is 1 minus 0.5 into z inverse and then 1 minus 0.45 into z inverse. That is, from this h1 of z is equal to 1 divided by 1 minus 0.5 into z inverse, and h2 of z is equal to 1 divided by 1 minus 0.45 into z inverse. So for this, I am going to find the new pole location for each transfer function h1 of z and the h2 of z. That is, for h1 of z is equal to 1 minus, that is a quantization value of 0.5 into z power minus 1. So you have to apply the quantization for 0.5. That is, you just convert the decimal into binary. So how to convert into decimal into binary? 0.5 into 2, 1.0. That is again 0 into 0, 0. It goes like this. So the conversion is 0.100 like this, and then do the 3-bit truncation. So after 3-bit truncation, it is 0.100. Again convert this value into decimal, that is multiply by 2 power minus 1, that is 1 into 2 power minus 1, 2 power minus 2 and 2 power minus 3. 1 into 1 by 2, 0.5. 0.5 base 10. And similarly, h2 of z. So h2 of z is equal to 1 minus quantization of 0.45 z power minus 1. So for this, again convert 0.45 into decimal, that is 0.45 into 2. 0.45 into 2, that is 0.9. 0.9 into 2, 1.8. 0.8 into 2, 1.6. 0.6 into 2 is equal to 1.2. Take the values 0, 1, 1 and 1. So after conversion it is 0.01112. That is after 3-bit truncation, after quantization process it is 0.00011 base 2, and then you have to convert into decimal, that is multiply by powers of 2, that is 2 power minus 1, 2 power minus 2, and then 2 power minus 3. That is 0 into 2 power minus 1, 0, and then 1 by 4 plus 1 by 8, and it is equal to 0.375 base 10. 0.375 base 10. So from this, the new quantized value for h1 of z after quantization is 1 minus, for 0.5 it is 0.5 z power minus 1. Then for this I am just taking z power minus 1 common outside, so z minus 0.5, which is equal to z divided by z minus 0.5. So the poles is 0.5, and similarly for second, h2 of z is 1 minus 0.375 z power minus 1. It is equal to, when you take z common outside, it is equal to z minus 0.375. So the new, after quantization process, my new pole is 0.375. While comparing with the actual poles 0.5 and 0.45, the actual poles is 0.5 and the 0.45. When you compare with the cascade form realization, the poles are exactly at the 0.5 and 0.375. So while comparing with the actual pole and the after quantization process by using the cascade form, the poles is the actual pole is exactly the same after the quantization process, and the next pole is very close to the actual pole. That is, using cascade form, by cascade form, after quantization process, the poles are exactly the same. Poles are exactly same. I just briefed the problem. So this one is the effect of code word length due to the quantization of filter coefficient. First, before start the problem, first find the actual poles. Then in direct form and in cascade form, analyze the filter coefficient after the quantization process. For direct form, you just multiply the terms. After simplification, arrive the result in terms of first order and the second order. Do the quantization process. In the problem, it is given it as a 3-bit truncation. 3-bit, convert this decimal into binary just by multiplying it by 2 terms, and then convert after quantization process by 3-bit truncation, convert into binary. Again this binary after quantization again convert into decimal, multiply by 2 power minus 1, 2 power minus 2, and 2 power minus 3, and similarly do it for the another filter coefficient 0.225, the same thing. So after the quantization process, my new pole filter coefficient is minus 0.875 and 0.125. And then finding the new poles, by solving the quadratic equation. My new poles are 0.695 and 0.179. The poles are not exactly same. It is somewhat deviate from the actual value while realizing the FAR filter in direct form 1. Next one is the cascade form. In cascade form, I am dividing this in two transfer function h1 of z and h2 of z, 1 divided by 1 minus 0.5 z inverse, 1 minus 0.45 into z inverse. For h1 of z, the quantization process, the same process for 0.5 after quantization it is same, and similarly for 0.45 the quantization is 0.375. When it is compared with the actual value, there is no much difference in the actual value. So by cascade form, the poles are exactly same. There is no much deviation in the actual value. Thank you so much. Thanks for listening. For more problem, subscribe our channel. Thank you so much.